Great. So it's a pleasure to welcome Professor Klaas-Jan Tielrooij to Singapore, I guess, virtually at least, to our condensed matter seminar series. Klaas is an expert in ultrafast techniques, so he's kind of done the full range of various ultrafast things that range from, I just learned, water molecules all the way to quantum materials like graphene and other things. He's an expert in these techniques to actually try to unveil the inner lives of electrons so they kind of move around. And he's recently he made a big name for himself at ICFO in Barcelona, and then now has actually moved to start his own group at ICN2. Is this where Sergio is? I guess.
Yes.
Yeah. So yeah, that's right. So he's owned an independent group for a number of years now. We won a very big grant, so it's a very big lab. And so without further ado, let's welcome the class to give this condensed matter seminar. Thank you very much, Klaas, for coming.
Okay, thank you very much, Justin, for this introduction, and thank you all for being here. So yeah, as Justin was saying, I am located at ICN2. So this is the Catalan Institute of Nanoscience and Nanotechnology. It's located in Barcelona, Spain. You can see a little picture of Barcelona beach here. The institute is quite far away from the beach, but it's still close to Barcelona. Nice sunny place. And this is my group. So we're quite a few people now, and we're mainly interested in understanding and also exploiting ultrafast dynamics in nanoscale systems. So our angle is really trying to understand the fundamentals, but then also try and see if we can do something applied with the things that we discover. And if you want to know more about the group, here's the website. It's ultrafastdynamics.com. So one of the topics that we're interested in, and then I'm going to talk about today, is understanding and exploiting heat in quantum materials. So I will take a broad definition of quantum materials. So this includes all the layered materials. And we all know they have all these very fascinating electrical, optical, magnetic, mechanical properties. Including the fact that you can stack them within atomic proximity on top of each other. And you have this new degree of freedom, which is the twist angle. And this gives rise to all kinds of interesting phenomena, electrical transport, magnetic transport, optical interactions. All these things have been studied a lot. And what I would like to figure out is, are there also interesting things happening in terms of heat transport? Is there anything interesting, and is there anything useful? And my goal is to convince you by the end of this talk that the answer to these questions is affirmative. So yes, it is interesting, and yes, it can be useful. So I will discuss mainly three topics. So the first topic is electronic heat transport in graphene. The second topic is Terra's nonlinear photonics with quantum materials. Doesn't seem to be related to electronic heat, but it is. And the last topic is actually trying to understand phonon heat transport in semiconducting crystals, layered crystals, all the way down to the monolayer. So for the first topic, I have to acknowledge people at ICFO, Manchester, Japan, and my institute. And in particular, Alex Block, a postdoc in my group, who did all the experiments. And also Alessandro Principi, who was responsible for the theory development. So, okay, we'll go through this very quickly. So we know all these fascinating properties of graphene: high charge mobility, ultra broadband absorption, the thermal conductivity of the phonons that is ultra high, and you can tune, of course, the Fermi energy, which you would do with a backgate, for instance. So you apply a voltage and that shifts the Fermi energy in your graphene. Now, I really like showing this one because it's from a collaboration with Justin, I think about a decade ago now. So this is
that's so long ago. Yeah, it's ridiculous how long. Yeah.
But it is a very important special property of graphene, which is the very efficient light-induced electron heating. And okay, we looked at this in a microscopic way. So you have the electron-electron interactions after you photo-excited it. And what this does is that you actually get a broadened Fermi dark distribution. So this is from some work we did a few years later, where we looked at it more from a thermodynamic perspective. So what happens is you absorb light, you get an increased electron temperature. And it turns out that this is very useful for several technologies. So one thing we showed a bit more recently is that you can use this for terahertz, detecting terahertz light. So what you see here is actually a terahertz focus, and you can resolve the entire array pattern. And that's quite remarkable. First of all, it means that you have a very nice terahertz focus, which is not so easy. Second of all, you have a very sensitive detector based on heat in graphene, because those array rings have very low intensity. So the fact that we can resolve this means that we have a very efficient detector. And that's for a large part due to this very efficient heating in graphene. It's also playing a very big role for future plans in data communication. So in particular for the photoreceivers, because it's a very sensitive detector, but it's also a very fast detector. And that's very interesting if you have fast oscillating signals between 0 and 1. So that's a very big topic actually in the graphene flagship, this very large effort within Europe to bring graphene into the marketplace. Now, the question I would like to answer is, are there also thermal applications? So there are definitely already some applications where they use phonon heat, but I'm interested in seeing if we can do something with the heat that is carried by the electrons. And that's now the main topic of this first part of the talk. And for this, we needed to actually develop a novel technique that didn't exist. It's quite a neat technique. So it has nanometer spatial accuracy, femtosecond temporal resolution. And well, the picture is a kind of artist impression by the postdoc who actually did the measurements. So you see some electrons moving around and some light pulses. But I will show you in a bit more detail how this works. So we start out with a sample that is basically a whole bar. So we can look at longitudinal and transverse currents or voltages. It's also a split gate device. So we have 2 of these back gates, which means that we can generate a PN junction halfway through the graphene channel that's in there. So I should mention that the final device we used was made at ICFO. So what we're now going to do is we're going to shine light in the left part of the channel. The light is absorbed, generates an increase in electron temperature, and then this heat will start diffusing. We do the same thing on the right side of the channel. So we create an electron temperature, this heat will start diffusing. Then eventually, this heat will meet up at the PN junction, where it's going to generate a local photothermoelectric voltage. That we can measure as a global photocurrent that runs through this channel. Now, what we're then going to do is we're going to change both the temporal offset between these 2 light pulses on both sides of the PN junction and the spatial offset. So the distance between where we shine the light and where we actually have this junction. And then we're going to do one more trick, which is that we're not interested in the heat signal generated by one of the 2 light pulses. We're only interested in the heat that's generated by both of them at the same time. So the interacting heat generated photocurrent. That's what we're interested in. And the trick we use for that is that we use a chopper to modulate with the frequency each of the pulses. They have a different frequency, and we look at the difference frequency. So that means we're only sensitive to how heat from one pulse affects the heat of the other pulse and then generates a photothermoelectric current. And then we're going to look at this as a function of changing time delay and spatial delay. You can, of course, imagine that if you increase delta X, you need to wait longer before the heat actually arrives to the junction. You can also imagine that the higher your diffusivity, the less you have to wait before it actually reaches there. So in that sense, by changing or by looking at the electronic heat flow in space and time, we can get information about the diffusivity. Now, you here see some raw data. So this is as a function of both the spatial offset in the y-axis and temporal offset in the horizontal axis. And in the color scale, you see the amount of this interacting heat signal. And of course, it's symmetric because it doesn't matter which pulse comes first. What you see that at around time 0, the signal is a bit less broad, and then it becomes broader the longer you wait. And that's just because, yeah, the longer you wait, the more heat can actually reach that junction. Now in white, you see marked the full width half max when we take a cut along the y-axis. So what's basically happening is that you see this widening up, and that is a diffusion process. So you can actually think of it as you dump heat in a Gaussian spot. This will start broadening as a function of time, and how fast it broadens will tell you what is your diffusivity. So we can map this out and plot it as a function of delay time, plot the width of this spatial cut. We can do this for different Fermi energies, and what you see is that we have the smallest width at time 0, and then it becomes broader the longer we wait. So that's this heat diffusion. We can look how this compares with what we would expect, because in the diffusive regime, this transport is governed by the Einstein relation. So you can also derive this from the Wiedemann-Franz equation, actually. That just says that heat transport follows charge transport. And you get this very, very simple, elegant equation. What's interesting is that we can actually also measure our electrical mobility because we have this whole bar device. So that means that we can predict the diffusivity that we would expect for our device. So these are the mobilities that we measure. Well, I'll plot them in terms of momentum relaxation time, but it's kind of the same. And as a function of Fermi energy. So we get something on the order of a few hundred femtoseconds of momentum relaxation time. That corresponds to mobilities on the order of a few 10,000 centimeters squared per volt second. So these are relatively high mobility samples. They're BN encapsulated, but they're at room temperature. They're kind of standard BN encapsulated graphene devices. And you can then get a diffusivity prediction that's on the order of 1,000 centimeters squared per second. We can plug this into our system, plot this diffusivity, and you actually see that it matches the data quite well. So that means that in the diffusive regime, everything seems to make sense. So just to make sure you understand the shape, we can also just plot the diffusion equation with a minimal width at time 0, and then just a linear slope that is governed by twice the diffusivity. And you see that that explains the initial slope. And then, okay, we see some flattening at longer delay. That's because of the finite size of the device. And that's fully captured by our simulation. So we simulate the entire nonlinear photocurrent experiment, plugging in these diffusivities. And that's how you get then this blue dashed line. And also these solid lines that describe the data very well. So this means that we have this diffusivity on the order of 1,000 centimeters squared per second, which is nice. In terms of thermal conductivity, this corresponds to something on the order of 100 watt per meter Kelvin. So that's just plugging in the electronic heat capacity. We're multiplying the diffusivity with the electronic heat capacity. And that corresponds to some theory works on graphene, which also predicts something on the order of 100 watt per meter Kelvin. And that's lower than what the phonons do in graphene. So the phonons can have more than 1,000 watt per meter Kelvin.
And so these phonons are acoustic phonons.
Yes, mainly, yeah. We'll come back to that a little bit in the last part of my talk when we look at phonon transport in TMDs, actually. Yeah, so is this then the end of this story? So it all makes sense. There's actually still something interesting here, and that is what's happening at time 0. Because what I was plotting here in terms of simulation is what we were expecting also in terms of where the signal would start at time 0, because this is the convolution of our two pump spots. So there's something really fast happening around time 0. And it seems to depend on Fermi energy. So the lower you go in Fermi energy, the higher it starts. And that's a bit surprising because a lower Fermi energy actually has a lower mobility and therefore lower diffusivity. So what's happening there around time 0? Now for that, we need to realize that we're in a very special regime. We're in a regime where we're looking at a time scale that is longer than the electron-electron interaction time, which is on the order of tens of femtoseconds. Our time resolution is, let's say, 100 femtoseconds. But we're looking at a time scale also where we are faster than the momentum relaxation time, because this is a few hundred femtoseconds. So we're looking at a time where only electrons interact with each other. They're not interacting with impurities and not with phonons or anything, or disorder. So we're looking at a system where only electrons are interacting with each other, not with anything external. So I think probably I can go quite quickly through this, as most of you probably notice. So there's different transport regime, diffusive regime, where you have a mean-free path. Then you have the ballistic regime, where you make your system very small. So electrons move in straight lines and only scatter at the interface. And then there's the hydrodynamic regime, which you can see as the electrons just becoming really big balls because they're mainly sensing each other rather than other types of entities like phonons or disorder or whatever. So people usually think of this in terms of transport. So that's why they think of length scales. But we tend to think in time scales, but it's completely equivalent. So we have a system where our time scale is somewhere in between the electron-electron interaction time and the momentum relaxation time. And that means that we're in this hydrodynamic regime where you have strong electron-electron interactions and viscous flow. Now, this has gotten quite some attention over the last couple of years, but again, mainly in transport. So you get these kind of funky whirlpool-like heat flow or charge flows in this regime. This has been studied quite a lot. I don't list all the papers here. So there's one last complication to this story, which is that there's two regimes within this hydrodynamic regime, and that's the Dirac fluid and the Fermi liquid. And to know in which regime you are, you need to look at the electron temperature with respect to the Fermi temperature. So the Fermi energy divided by Boltzmann constant. And the big difference lies in the fact that if you're in a Fermi liquid, you have a relatively low electron temperature compared to the Fermi temperature. So you still only have, let's say, electrons in the valence in the conduction band. Whereas in the Dirac fluid regime, you can have such a high electron temperature compared to your Fermi temperature that you actually start creating also holes in your valence band together with the electrons in the conduction band. Now, in terms of heat transport, there's been some work, especially this seminal paper by the Philip Kim group, and where he saw breaking of the Wiedemann-Franz law extremely close to the Dirac point at reduced temperatures. So what he sees is that heat transport there is faster than charge transport. But that disappeared at a certain temperature, mainly because their technique didn't work anymore. And they required extremely clean samples. They needed to go extremely close to the Dirac point. So what's interesting about our technique is that we have these control knobs that allow us to tune all the way through this phase diagram. So we can tune the electron temperature using our laser power, and we can tune the Fermi energy with these backgates that we have. So let's try this. So I show here the most extreme cases. So on the most left and the most right, we have low electron temperature and high Fermi temperature. So that's the Fermi liquid regime. You see relatively small spots. So this is just scanning at time zero through our PN junction. Well, actually, it's a little 2D image. So you see a relatively small spot. So that means relatively little heat spreading. Then if you look at high electron temperature and low Fermi temperature, which is the middle two graphs, you see a broader spot. And none of these data are normalized because it turns out that you get relatively similar photocurrent signals in these two regimes. So you can really make a very fair comparison without any artifacts by just looking at these data. And I'm pretty sure you will agree with me that the center ones are larger than the outer ones. So that suggests indeed that there's more heat transport in this regime. So now we can tune all the way through the, sorry.
Hi, if you can go one slide back. So how about if you have high TE and also high TF?
That will be on the next slide, actually.
Oh,
so,
sorry. Okay.
So, yeah. So that would be somewhere in this top left corner or top right corner. So then it really depends on how high is your electron temperature and how high is your Fermi temperature.
Okay, thanks.
Yeah. So indeed, the idea is like, how much do you get into this regime where you get the coexistence of holes in your valence band and electrons in your conduction band.
I see. So the point here is not so much to probe the hydrodynamic regime, but to probe the fact that you could have a coexistent electron hole kind of gas liquid or something.
Right. Right, because that's the regime where you get this. So what basically happens is that if in that regime you apply an electrical gradient, the electron and holes are moving a different way. So that means it's viscous flow, it's not very conductive actually. But it turns out that under a thermal gradient, they will move in the same direction, both the electrons and the holes. They do this at the same speed without changing direction because they're not interacting with anything. And they're also not interacting with each other because they're kind of moving with the same speed along the same direction. So theoretical predictions are that if you're in the perfect Dirac fluid regime, thermal conductivity goes to infinity. It basically diverges. There must be some limiting factor there that will kick in at some point. But yeah, the theoretical prediction is that it basically diverges. So this is the regime one would need to reach, so the coexistence of electrons and holes. There are theoretical predictions. When is the crossover? We use here this very simple relation that once your electron temperature is higher than your Fermi temperature, you're probably kind of into this Dirac fluid regime. So that's this purple dashed line that indicates the difference between the Fermi liquid and the Dirac fluid regime. And indeed, you see in this map, so this is two different measurements, one where we're scanning across the PN junction and one where we're scanning along the PN junction. And each of these data points is a line cut where we then extract the broadening. And the color indicates the amount of broadening. You see that the closer you get to the Dirac point and the higher you get in electron temperature, the more you get into these reddish colors, which means more broadening. So this is all very consistent with this picture that you're tuning your system in this hydrodynamic regime from the Fermi liquid into the Dirac fluid regime. And this is a real, it's a quantum critical phenomenon. So it's a phase transition at zero temperature. But we're looking at this at room temperature and electron temperatures that are way above room temperature. So I think that's quite interesting. We also did some, so again, this is this phase diagram that we're tuning through. So it looks very similar. So we went into a little bit of theory on this together with Alessandro Principi. So he was actually visiting my lab the last 2 weeks. So this is a picture of him in front of his office at ICN2. In any case, so he did the full Dirac fluid theory, and he calculates how the thermal diffusivity evolves as a function of the same parameters, so electron temperature and Fermi temperature. And then from this diffusivity that he calculates, we can calculate the amount of broadening we would expect. And that's what you see here in the color map. And you see pretty amazing numbers. So once you get really in this regime where we start seeing these red colors of strong broadening, he predicts diffusivities on the order of more than 100,000 centimeters squared per second. So that's more than 100 times larger than what you have in a normal diffusive regime. So what is then the picture? So this is the picture that we then reach. So around time zero, you have a short-lived period of time where you have this extremely large diffusivity that just really brings up this initial data point, because we cannot resolve this initial broadening because our time resolution is not good enough for that. So we just see it as a larger minimum point. But if we would draw here this line of 100,000 centimeters squared per second diffusivity, after a few hundred femtoseconds, it brings you exactly up to this point where we see our data starting to then diffuse in the diffusive regime with a much smaller slope. So we have this short-lived period of time where we have 100 times or more higher diffusivity. Another way to look at this is if you're in the Fermi liquid regime, at time zero, you generate this hotspot that might spread a little bit ballistically for, let's say, 200 femtoseconds. And then after 400 femtoseconds, it just starts spreading out diffusively because you're actually scattering. Then in the Dirac fluid regime, you have this short-lived period of time where you have this, this Dirac fluid flow, which we indicate with this wiggly line. But that's this regime where your electrons and holes are not scattering, and they're moving along the same thermal gradient and leading to very large spreading. And after that, you get back into the diffusive spreading. So this is the interesting regime marked here. So this is where you actually have this very high thermal diffusivity, but also a very high thermal conductivity, because also the electronic heat capacity is large. So I actually get on the order of 40,000 watt per meter Kelvin thermal conductivity. So that's another order of magnitude larger than the already record high thermal conductivity of the phonons in graphene. And theoretically, there were predictions already of even 100,000 watt per meter Kelvin and diverging. It's just a matter of how close can you get to the Dirac point and how high can you make your electron temperature.
That's very interesting. So actually, I have lots of questions, but could I just quickly just ask, maybe ask more questions at the end, but
sure.
Did you actually see the 40,000 watts per?
Yes. So well, the 40,000
extrapolation, because if you went back like 2 or 3 slides, you had some other number there, and it wasn't. Yeah. Sorry. Just one more slide. Yeah. Yeah, so you measured sigma x squared, right? So it seemed, for example, that you basically only saw 1.4, and this is 1.8, and you know, this is 5 microns, right?
Yes. So but if you look at the regime,
right? Yeah.
Yeah. But that red part is like approaching 1 million. So if you look at the 1.8. We're in this color scale that's a bit, let's say, orangey. So that does get into the regime of 100,000. So we did also extract from the data the diffusivity. So we can look at the sigma x squared at time 0 and the sigma x squared that we expect from the convolution of our 2 spot sizes. Mm-hmm. And then you can take a time scale, which we take our time resolution. So I think it's on the order of 150 femtoseconds. Mm-hmm. So by using these 2 widths and the time scale, you can also extract from the experiment directly a diffusivity, and the number we get is up to 70,000 centimeters squared per second.
Wow.
So we don't directly see the 100,000, but we get up to 70,000. For not for this device, for a different device. This device went up to, I think, 45,000.
I see.
Yeah.
Okay. Thanks very much.
Yeah. And then the thermal conductivity we don't measure directly, but we need to plug in the theoretical value for the electrical heat capacity. Yeah. So yeah, these numbers seem to make sense with what's predicted in theory. And we think these numbers are also very useful for heat management, for thermal management, to avoid your computer chip looking like this. Of course, not for microscopic things, but in a lot of these devices, it all starts out with one little hotspot where you then get breakdown, and then the whole thing gets worse. So if you have nanometer-sized hotspots, it's very interesting if you can, within hundreds of femtoseconds, have graphene sitting there to spread out this heat already by order of a micron, because you can see here that at time 0 we already have several microns of broadening. So it's such a high diffusivity. It's short-lived, but if you in that very small amount of time, it can still broaden by a micron. So we think it's very interesting to avoid detrimental effects of nanometer-sized or tens of nanometer-sized hotspots in electronic devices. So with that, I would like to go to the next topic, if that's okay. So the next topic is will be a little bit shorter. So the other 2 are both a little bit shorter. So I think we'll finish in time. So the next topic is nonlinear photonics with quantum materials. For this, I especially need to thank people at the Helmholtz Center in Dresden, where the experiments were done, especially Sergei Kovalev. And this whole field of nonlinear terahertz photonics we did together with the group of Professor Dmitry Turinovic, who is now in Bielefeld, who used to be in Mainz. So he has been one of the main driving forces behind this. So again, this relies on the special property of graphene, that is the efficient light-induced heating. So this broadening of the Fermi dark distribution. But now we use the fact that this broadening doesn't only happen when you create electron hole pairs across the bands, but it also happens when you just accelerate your charges using this very low photon energy of terahertz light. That's one element that goes into the equation, let's say. The other element is the following, which is that, and that's what you see here in this graph. So if you have a relatively low field strength, you have more than 10% absorption of your terahertz light. That's because in this case, you're not governed by the universal 2.3, but you're governed by basically the intra-band absorption, Drude absorption. So the higher your mobility, the higher the absorption, and the higher the Fermi energy. So in our case, it's almost 12%. But then the more field you start putting into your system, the more you start absorbing light, the less absorption you get. And that is because it turns out that the hot electron system has a lower terahertz conductivity. That's something we've also studied in quite a lot of detail, including with Justin. And here you see that directly, but this is very interesting because this is a terahertz nonlinearity, because you change the terahertz absorption by adding more terahertz power. And that is, by definition, a terahertz nonlinearity. And that's something that we can use to generate harmonics, which is a canonical example of nonlinear light-matter interactions. So I show that here. So we have a graphene sheet, just simple CVD graphene. We come in with an oscillating electric field, in this case 300 gigahertz, with a field strength up to 80 kilovolt per centimeter. And what happens is that while light is being absorbed in the graphene, it starts absorbing less. So the polarization doesn't follow exactly the electric field, but it starts saturating, it starts tailing off, and that gives rise to a nonlinearity. In this case, only the odd nonlinearities, because it's centrosymmetric. And that in turn gives rise to the generation of harmonics. So we actually measured that directly. So both of these are measured traces. So both the incoming light pulse and the outgoing light pulse is measured. That's the nice thing about terahertz radiation. You can measure it through electro-optic sampling, and you do not get just the intensity of the light, but the full evolution of the electric field. And you already see directly that this is oscillating faster. And of course, we filtered out the fundamental because otherwise it would overshadow. And but you really see that this is oscillating 3 times faster than the fundamental. And if you look at the numbers, it's already approaching a kilovolt per centimeter. So that is pretty high efficiency for a single atomic layer of thickness. And in fact, in that first experiment, we already saw up to the 7th harmonic. Of course, you need to put more and more filters in there to resolve this and integrate for longer, but you can resolve up to the 7th harmonic. And we extract nonlinearities, nonlinear susceptibility on the order of 10 to the minus 9 meters squared per volt squared, and a conversion efficiency approaching 1%. Just to put this in perspective, if you look at graphene in the infrared regime, the nonlinear susceptibility is 10 to the minus 18. So that's 9 orders of magnitude lower. So definitely this system is very efficient in its nonlinear properties in the terahertz regime. The question is, can we do better? And that's what we tried here. So we generated the grating graphene metamaterial. So we put metallic stripes on top of the graphene. And we came in with relatively low field strength. This is on the order of, I think, around 10 kilovolt per centimeter. And maybe good to point out, so normally when people do nonlinear optics, even in the visible, where efficiencies are very high, the light source is also much brighter. So people tend to see all those nonlinear effects using megavolts per centimeter of field strength. Here we're talking kilovolt per centimeter. Yeah, this is 10 kilovolt per centimeter. We shine it through bare graphene. You might see a little bit of an oscillation in the Fourier domain. You might want to see the third harmonic if you want, but it's not very large. Now, if you do this on the grating metamaterial, you see very clear oscillations and a very clear peak at 3 times the fundamental frequency. So you do get this enhancement of harmonic generation just by putting the metal grating on top. And in fact, we extrapolate that we get about 40 times enhancement at the lowest field strength. And then the higher you go in field strength, you get some saturation effects that I will briefly talk about in a bit. But what's important is that we've enhanced the nonlinear susceptibility by more than an order of magnitude. And this means that we're increasing the intensity of the third harmonic by more than 3 orders of magnitude. So we're generating a lot of harmonics here. And we can get an idea of the field conversion efficiency by measuring simultaneously the fundamental here at 0.3 and the third harmonic at 0.9. And you see that it's about 2 orders of magnitude lower. So it's about 1% conversion efficiency. Now, just very briefly, what's really interesting is that you enhance the higher harmonics even more with this metallic grating, because what the metallic grating does is just field enhancement within the gap between the pieces of metal. And that means that if you increase the electric field by a certain factor, the final harmonic goes with the power of that harmonic. So basically, if you have a field enhancement, in our case, it's about a factor 5. That means that the third harmonic is enhanced by 5 to the power 3. So that's 125, but you also have less active area because part of your sample is covered by this metal. In fact, most of it is covered by the metal, about 90%. So you also have to account for the fact that only 10% is actually active area. And for the field enhancement, this goes with the square root. So you have a factor 3 there. So it's 125 divided by 3. So you get with this 40 times enhancement. But if you look at the higher harmonics, it's not just 5 to the power 3, but for instance, for the 9th harmonic, it's 5 to the power 9. And then this factor 3. So that's really in the ideal regime of the non-perturbative regime, which we never reach because we put quite a lot of field strength in there. So in this simulation here, we accounted for some of the saturation effects, but still you see that, for instance, for the 9th harmonic, this grating would enhance by many orders of magnitude the amount of generated harmonic. So we tried this experimentally. So we come in with relatively low field strength, only 30 kilovolt per centimeter. Put a lot of filters. So you definitely see the 5th harmonic, you see the 7th harmonic. And if you're a little bit forgiving, you might see the 9th harmonic, but definitely up to the 7th harmonic, we're generating with a laser-based source. So that's just tabletop, relatively low field strength, and we see up to the 7th harmonic with a monolayer graphene with a bit of metal on top. This I just want to flash really quickly. We can also, of course, the typical graphene thing, you can control this with an electrical voltage. So we can put an electrolyte on top. We can tune by an order of magnitude the amount of third harmonic generation just by moving the Fermi energy. And it's kind of you're changing the amount of terahertz absorption mainly, but that works. So we have quite a nice toolbox of nonlinear photonic techniques. So we can generate all these harmonics, we can enhance the nonlinearity, and we can electrically tune it. So there's just one little issue that we still need to solve, which is this saturation. So this is something we don't want. We want ideally this nonlinear susceptibility to stay constant, because then the more power you put in, the more power you get out. And that's not what we're getting. This limits the overall generated harmonic power. And that actually happens especially in the case of graphene. So you see here in black, that's graphene. With the grating, it completely saturates at some point. So we started looking at other quantum materials. So there's these very nice topological insulators, which have, as graphene, massless Dirac electrons at the surface, which can also heat up and can also generate harmonic signals. And in fact, they start outcompeting the graphene. So this is for a bismuth selenide sample with low Fermi energy, and we can get orders of magnitude larger harmonic generation than graphene in this regime of very large incident field strength. This is still unpublished results. We're about to submit it, I hope. And the explanation we have is the following. So in graphene, we know that there's a lot of heat accumulation. So you start first heating up this electron system tries to cool down to the phonon system, optical phonons, acoustic phonons, but at some point, the phonon system cannot get rid of its heat fast enough, and it starts to heat back up the electron system. And all this accumulated heat doesn't help for harmonic generation, because you kind of need heat accumulation, but then you also need these heating cooling cycles following your incident terahertz field. Otherwise, you don't get an oscillating polarization that generates the harmonic. So that's the problem of graphene, that it starts to accumulate heat. And that's a problem we don't have in the TI, because you have very efficient Coulomb interaction between the surface electrons and the bulk electrons. So this means that you get very efficient heat dissipation. So you keep getting these heat and cooling cycles, even in this regime of very high intensity incident light. So it keeps generating harmonics, and it even increases further than graphene. So also for the theory behind this effect, we collaborated with Alessandro. I think he's actually visiting next week. No?
Yes, that's right. So he's giving a talk next week as well.
Right.
Yeah.
So he might tell you more about the underlying physics of.
Yeah, better. Yeah, very good.
So yeah, just to summarize this part, so we get this very efficient harmonic generation. We can make it even more efficient using this grating metamaterial. We can electrically tune it, and we get now up with the TI up to 10% field conversion efficiency for the third harmonic, and a nonlinear susceptibility of 10 to the minus 8 or tens of ESU if you prefer those units. So that's quite interesting for applications in the terahertz regime, such as in homeland security, data communication, diagnostics, and things like this. So that brings me to the last part of the talk, which I think we'll manage to do within time. So this is about phonon heat transport. So everything we've discussed so far is mainly electron heat transport. Now we're going to turn to the phonons. And this, I especially have to acknowledge people in my group, so David, Sabin, and Roberta, who did both the experiments in the theory. And also the theory was developed together with Mathieu Verstraeten in Liège. And there were other people involved. Most of the experiments were done in the lab of Clivia Sotomayor at ICN2. So the idea of this topic is to understand what is different in heat transport between a 3D bonded material like silicon and a 2D bonded material like MOSE2. Now, and then especially what happens if you change the thickness of these materials. So people have made silicon films down to a few nanometers. We managed to make in our lab MOSE2 films down to molecular layer, a single molecular layer. So that's sub-nanometer thickness. It's kind of interesting. Sometimes they're a bit wrinkled. We can iron them out to get a really nice film suspended over 50 microns, which is, I think, the largest I've seen in literature. And now comparing to silicon, what happens in silicon is that the thermal conductivity decreases a lot when you make this material thinner. So silicon has a pretty high thermal conductivity if it's bulk, 150 watt per meter Kelvin, but it's pretty low when you get to 10 nanometer thickness. And that's not good if you want to make devices out of this. And you cannot get below this 10 nanometer very easily. It's very challenging to fabricate this. So with 2D materials, we can reach that regime all the way down to outside this graph, the sub-nanometer regime. So we did this with MOSE2. Okay, there's some literature results, and it's not very clear. So some people predict that it's going down with thickness and then maybe even going up again. In theory, people had only looked at monolayer or bulk, and especially for the monolayer, there's a large spread. So it's not really clear what the trends are. So that's something we wanted to address. This is how we do it in the lab. So we build our own transfer system. We can make these suspended materials. TM images show that they're very nicely monocrystalline, and they're extremely flat and clean. So you see here the suspended region has sub-nanometer roughness. So it's really very clean, nice samples. We can confirm that it's monolayer through photoluminescence. So samples look nice. And now what we're going to do is look at heat transport. And we're going to use a technique that is called Raman thermometry. So the way this works is that you have your suspended monolayer or your suspended multilayer, whatever. You shine light in the center, that heats up. That heat will start spreading radially and then heat sink into the substrate at the edge of the suspended region. And then with the same laser that we're heating up, we're also going to look at the Raman scattered signal. And then the peak position will be our marker, an indication of the temperature of the crystal. And this we can calibrate by just heating up the stack or the film and looking at the position of the peak. So we know which peak position corresponds to which temperature. And then from the temperature as a function of incident power, we can extract the thermal conductivity using this equation. There's basically two geometrical factors. One that is this alpha, which is around 1. Another one that is this relation between your hole size and your spot size. And then it's just a matter of how much is your temperature increasing with your increasing power. And then, of course, the thickness also comes in there. So basically, the less your temperature increases with power, the higher your conductivity, because it's moving the heat faster to the heat sink. That's the idea. So we did this measurement for a lot of different samples with different thicknesses. And you see that they very nicely line up according to their thickness. That is when you plot the temperature increase as a function of absorbed power. So basically, to heat up by the same amount a thicker film, you need to add a lot more power. That makes complete sense because there's more material to share the heat. So what makes more sense to look at is looking at this, but then multiplied by the thickness. So basically, we correct for this term in this equation. So already got something that is indicating, so where the slope is indicating the thermal conductivity. And you see that it doesn't change by that much when we multiply by the thickness. So there seems to be a pretty weak effect of thickness on the thermal conductivity. So how weak is this effect? Well, it's really quite weak. So we now extract through this equation the thermal conductivity, and we get something on the order of 20 watt per meter Kelvin for this whole range of monolayers up to several tenths of nanometers, or several tenths of layers, which is several tenths of nanometers. Important to note that that's something people didn't do in the literature so far, but for us it was really important to make multiple samples, measure them in multiple independent runs, because it's very easy to have some contamination and it will completely give you the wrong value. So the fact that, for instance, we have 4 independently made and independently measured bilayer samples that all end up somewhere just below 20 watt per meter Kelvin is a very good indication that we have very reproducible samples and a very reliable extraction of the thermal conductivity. So this looks very different than silicon. So at silicon, already at 10 nanometers, you're at lower values. Here we have a constant value throughout this entire range. So for bulk, people are expecting around 30 watt per meter Kelvin. So if you would put the same trend in this graph for silicon, you see that it's much more flat.
So Klaas, just to make sure I understand completely, when you're talking about this left-hand side panel, which is this layered material for MOSE2, you're talking about thermal conduction through the layers, right? This is the
in plane.
So this is in plane, but did you measure the out of plane stuff?
Not yet. So in our case, the out of plane does not play a role because we shine light to heat up in the center of the suspended film.
I see.
And it gets heated up uniformly throughout the entire flake.
I see. And in the case, for example, of this thin film of silicon, is that in plane or out of plane?
It's also the in plane thermal conductivity. Yeah.
I see. Okay, so it's apples to apples. Okay, very good. Thanks.
Yes. Although, you'll see that it's slightly different, and it has to do with in plane versus out of plane phonon movement. I will show that in a little bit.
Okay, thank you.
So just to figure out if this also made sense, we started a collaboration with Mathieu in Belgium, and Roberta, postdoc in my group, she did ab initio simulations of thermal transport, and what's very important is she managed to do this at room temperature and even higher temperatures. So normally ab initio is done at 0 Kelvin. And here, by combining siesta with a special package, we get the thermal conductivity at elevated temperatures. And those are the diamonds. So we plot the number for 400 Kelvin because that's mostly, the most fair number to compare with our experiment, because we heat up by on the order of 100 Kelvin in our experiment. So you see that the numbers up to 6 layers correspond quite well. And we also get the bulk value, which is a little bit higher than 30 watt per meter Kelvin. Which is something we didn't access experimentally, because then you do get the problem that you only heat up the top part and you need to account for out of plane. But we get very good agreement between theory and experiment, and we can use the theory to understand what's going on, because what actually happens is that you are losing phonon modes while you're thinning down your sample, because you just have fewer atoms, fewer interfaces. So you're losing modes. So that means that if you look here, this is a plot of basically the spectrally resolved contribution of modes to the thermal conductivity. So you see that for bulk, it's mainly modes around 1 terahertz that correspond to the thermal conductivity. So these are interlayer modes, mainly, and mainly acoustic, although some of them also have an optical character. So it's a little bit difficult to say exactly what the modes are. So what happens is that when you thin down the sample, the crystal, you start losing some of those modes just because of having less material. But what's happening is that this decrease that you would then get in the thermal conductivity is compensated by the appearance of new modes at very low frequency. So these are like flexural type modes at very low frequency that can carry significant amounts of heat and compensate the fact that you're losing some thermal conductivity that used to be carried by these higher frequency modes. So the fact that you see a relatively constant thermal conductivity is not because nothing is changing, it's because you get compensating modes that in the end result in a relatively constant thermal conductivity. One other interesting thing we get from the theory is that for the monolayer, you actually get a quite large fraction of heat being carried by these low frequency modes, which also have very long mean-free path. So up to almost 50% of the heat is carried by modes with a mean-free path on the order of a micron or more. So that's quite remarkable, that you have these long mean-free paths. It also means that it's very important to have large enough samples. So in the literature, a lot of samples were on the order of a micron in size. That means you're limiting the mean-free path by your sample geometry, which is not what you want. So very quickly, because I think we need to wrap up, we saw one more interesting effect, which is, of course, what we've done so far is the in-plane thermal conductivity, but we can also look at out-of-plane heat dissipation. When we do not measure in vacuum, but we actually have air molecules there or nitrogen molecules, we see that you don't see a big difference when you have many layers. But when you go to the monolayer regime, you actually get a much larger apparent thermal conductivity. And that's because you now have a parallel channel where heat is not only moving in plane and then heat sinking, you're actually transferring heat to the air molecules in a very efficient way. And because it's only monolayer thickness, this can be quite efficient. So this is also something that we're not sure if everybody in literature was actually measuring vacuum. So if you do measure this in air, you might get a very high thermal conductivity, but it's not your real in-plane thermal conductivity. It's actually mostly out-of-plane heat dissipation. So that's a summary of this part of the talk. So we see this fairly constant in-plane thermal conductivity and this additional effect of very efficient out-of-plane heat dissipation to air molecules. And now the picture of this comparison between silicon 3D bonded and MRC2 2D bonded is the fact that when you have silicon, you have a lot of phonon modes that are diagonally moving through your film. So they're scattering at the surface, and then the thinner you make it, the more they're scattering at the surface. And this is what limits the heat transport and the thermal conductivity in 3D bonded materials. In 2D layered materials, already in bulk form or thick form, most of the heat transport is in plane because you have kind of internal interfaces. So the heat already doesn't want to, and the phonons don't want to have a lot of diagonal movement. There's a lot of movement in plane. And that is the reason why on top of the compensating phonon modes, you do not get a large decrease in thermal conductivity when you thin it down all the way to the monolayer. And we think this is quite interesting if you think about applications where you actually require an extremely thin semiconductor. Because compared to silicon, MRC2, for instance, it's not performing better in terms of thermal conductivity or electrical conductivity in bulk form, but it's outperforming silicon for both if you go to very thin films. So I think there's definitely interest in these materials for such applications where you need very thin films. So I'll just leave this slide here with the summary of everything I talked about. And with that, I would like to thank you all for your attention.
Thanks. It's a very, very good talk. Questions from people, especially students. postdocs as well.
I think there might be a question in the chat, or
yeah. So I think that one thing in the chat
that's...
was for people to take attendance. So that's the thing there. But please, anyone. Don't be shy.
This is what happens often with these online conferences and meetings. People are always a little bit
well, you know, sometimes people, and it just depending on the crowd, sometimes people can ask questions and it can be a bit more lively, I think. But yeah, just don't be shy, anyone. Just kind of ask questions. Okay, let me just ask a rude question. Okay, so let me be rude, and I apologize for being discourteous. So in the very first thing that you talked about, this electronic heat transfer on graphene, and there was a little bit of a discussion of hydrodynamics, right? And so what do you really mean by that? So, you know, there's a competition, especially when you're kind of, you know, shining with a very intense laser beam, you would basically heat it up to very high temperatures. Very high temperatures, usually, you know, what happens at high temperatures is that, you know, there's a competition between, in hydrodynamic regime, you basically want the electron-electron scattering or electron-electron momentum scattering type of mediated processes to dominate over all other processes, right? But at high temperatures, you know, you can easily leak out this momentum to say phonons, for example. And so what's that competition like, and why would you expect to see hydrodynamic, you know, behavior at ultra short timescales, especially with ultrafast?
Yeah, I think that's not a rude question. That's a very good question. So of course, what I was saying is that we use the momentum relaxation time that we measure with DC transport, which is a few hundred femtoseconds. So considering that time scale, we're very clearly in a hydrodynamic regime with our 100 femtosecond time resolution and the tens of femtosecond electron-electron interaction time. Now, the big question is, what happens with this effective momentum relaxation time when you consider the increased electron temperature? So does it get on the order of 200 femtoseconds, 150 femtoseconds, or 40 femtoseconds? So from what we're seeing is that it is still long enough to be in a hydrodynamic enough regime with our 100 femtosecond time resolution that you're not completely in the diffusive regime yet. But I agree with you that it's probably not so that we have 400 femtoseconds of momentum relaxation time, and therefore we have a hydrodynamic window of 400 femtoseconds. Because of the increased electron temperature, this window will be shorter.
More questions from other people? Maybe let me just press on this point as well again, if I could, you know, one thing kind of sticks and you kind of press on it. So what is the difference? You had a very nice figure about this with the thermal conductivity kind of stuff. You had, you know, both, you know, this Dirac liquid and this Fermi liquid regime, and then you said the hydrodynamic regime, there was this kind of coming out thing, and it was slightly different from each for each one, Fermi liquid versus Dirac liquid. What is the difference between ballistic spreading out straight away and this hydrodynamic thing, in particular in your case? So you're within this period, this very, very short window.
Yeah. So
is it just the same thing as ballistic, or is it something more? Is it like really a collective energy transport that requires actually a lot of scattering between? Like, I guess it does require electron-electron scattering. So because you're actually saying. You're saying that the electron-electron scattering is smaller than your time scale,
right?
And so you are trying to establish, you know, kind of a hot liquid or whatever, a Fermi liquid or Dirac fluid or something. So it's established. Momentum is kind of all kind of, you know, averaged out, but then it's below the Fermi. Okay, so it's different from ballistic,
right? So well within the hydrodynamic regime, if you're in the Fermi liquid regime, there's not much. it's kind of just ballistic because there's nothing special going on in these few hundred femtoseconds. So they're just moving in a straight line. Well, there's only electrons or only holes, so they're just moving in a straight line, and just their heat spreading. It can be a little bit faster than in a diffusive regime, but it's not as much as when you're really in a Dirac fluid regime. So this is where being in the hydrodynamic regime, and in particular in this Dirac fluid sub-regime, is important. And what's important is that there's no scattering between the electrons and the holes because they're moving along the same gradient and in the same direction and with the same speed, as far as I understand. I think Alessandro next week will probably give you a more detailed picture. But I think in the hydrodynamic Fermi liquid regime, there's no difference with ballistic because it's basically just a straight line, and it doesn't really, and then you just turn over into the diffusive regime after a few hundred femtoseconds. But in the Dirac fluid regime, there's really a difference because you get these electrons and holes coexisting, moving along the same thermal gradient.
I see.
And that's very distinct from ballistic because they would be going ballistically in a different direction.
Opposite directions, and very good. Finally, we have a question from somebody else. Singyu, do you want to ask your question in person, or do you want me to just read it out from in the chat? So it's in the chat right now. Maybe let me for the convenience of everybody. Oh, he has no microphone. So let me just read it out. Thanks for a nice talk. As far as I know, the highest thermal conductivity of graphene so far is around 5,300 watts per million Kelvin. But as you mentioned before, the theoretical thermal conductivity is extremely high. So can you explain why there is a big difference between experiment and theory? Is that because of defects in the sample, substrate, limitations of CVD? Thank you.
Okay, thank you for your question. Very interesting. So I think the important thing to realize here is that this number of around 5,000 watt per meter Kelvin is quite in agreement with theory, and it is heat transport where the phonons are carrying the heat. So there's definitely some debate about these numbers actually, both from experimental side and theoretical side. So graphene is not the easiest material because of all kinds of phonon anomalies to calculate its thermal conductivity. And experimentally, there's also room for artifacts. For instance, if you don't measure in vacuum, you'll get this out of plane, which will also happen for graphene. So there's a bit of debate about these numbers, but I think the general consensus is that, it's definitely around a few thousand watt per meter Kelvin. And this is kind of an agreement between experiment and theory. So what is the big difference with what I was showing is that here we have a short-lived amount of time where the heat is carried purely by electrons because they're not even interacting with the phonons. And in that short amount of time, you can have an even higher thermal conductivity. But this is not a steady state thermal conductivity or something. This is just something short-lived. But we think it's still useful for diffusing out hotspots in devices.
Hopefully that answered the question. So the key point there is, basically this 40,000 Dirac fluid kind of thermal conductivity actually is a short-lived time scale. So within this hydrodynamic window, it's not long time. In long times, you expect the phonons to take over, right?
Exactly.
Yeah, super fantastic. And maybe let me push on this point just to, I'm sure he would want to push on the same point here. So you say that this may be able to help, kind of dissipation of heat, kind of spreading it out. If this is only good in short time scales, is this the right time scale for?
I think it's long enough. So that's based on this picture that even if you start with, let's say, an initial spot of less than a micron, let's say a few hundred nanometers, within hundreds of within 100 femtoseconds, you've spread it out by more than a micron. So that means that if you go from 100 nanometers to a micron, that means a factor, let's say 100 reduce in temperature. If that whole temperature hotspot spreads out by a factor 10, that's a very strong decrease in temperature.
But only within the hydrodynamic window, and also only if the temperatures are high enough, right? Because you have this low T, high T thing, and
right. Right. So then the question is indeed, how high is this diffusivity when you are closer to, yeah, a few hundred? So here the lowest we got was like, I think 600, and it's still pretty substantial, but only if you're close enough to the Dirac point.
Okay.
So it will become more important to be really close to the Dirac point, so that it also works for relatively low, temperatures. Yeah.
Excellent.
This is something that we're actually going to be exploring. So we have a second ERC grant, which is called a proof of concept. So we're going to be exploring if we can actually exploit this effect in devices. And it will be a challenge, because you also need to actually couple that temperature in your device into the graphene.
Yeah.
Then again, we've seen in this other part of the talk that you can, for instance, couple very efficiently surface states of a TI into electronic bulk states. And so as long as you get close enough, Coulomb interactions can be very fast.
Excellent. Yes.
So we have good hopes.
Yeah, and I'd love to talk more about that at some point with you as well. Looks like you've answered his questions. Are there any more questions? If not, we can stop the formal part of this stuff. Any more questions, guys? Last call, final call. Going once, going twice. All right. So thank you very much. So I'm going to